Hello, in this video we're going to turn our attention to power and efficiency. So we've spent a lot of time up until this point, through our section on dynamics, looking at the effect of forces on matter and energy. So we've got our Newton's second law, F equals ma. That's giving us a relationship between force and motion here. So we've got force and acceleration and how they're proportional to each other. We've also looked at our work energy principle, where we've got the work done is the force times the distance. So we've got a relationship between energy in work done, so energy that's moved from one place to another, and the distance that a force is being applied through. So we've got this connection here between forces and energy and motion through the acceleration. Now, one thing we can see in Newton's second law with F equals ma is we've got time built into this, that the force is proportional here to the rate of change of the velocity. So we've got this dv dt in there, or the second derivative of the displacement. So time is built into this. We're saying with the force, well, how quickly is the motion changing? Whereas we haven't got that in our work energy principle. In the work energy principle, we're just saying, okay, well, we apply a force through a particular distance and we've got a transfer of energy. But how quickly are we doing that? I mean, we could be very, very slowly, moving something. We don't really know how quick the energy is moving from one place to another. I know we can get that by tying it into Newton's second law, but we've got this slight sort of detachment here in our descriptions at the moment of relating energy transfer with force. So this is now where we're coming into power, because we're looking here at the rate of transfer of energy, rate of energy transfer. So how much energy is being moved per unit time from one place to another. So that's what we're looking at with power, and we'll talk about that in more detail in a second. And then we've got efficiency, as in how much of the energy is actually going where we want it to go to. There's one thing just having energy thrown around all over the place, like you've set off some kind of bomb, but how much of it is going where you actually want. So these are the two things that we're going to be looking at in this video. Okay, so the rate of energy transfer. Pretty much everything that we look at of interest in physics is when you've got energy moving from one place to another. I mean, there are going to be a few exceptions, but for the most part, interesting things that are happening involve energy being moved from one place to another. So we need to really want to quantify, well, how quickly is this energy moving around and where is it going from and where is it going to? Now, there's going to be a lot of different ways of doing this. I mean, we're in classical mechanics at the moment, so we're looking at very mechanical, macroscopic examples in the real world, and that leads us to a certain type of analysis. We'll see how things will be different when we get onto things like electricity and such like in future topics. But at the moment, let's stick in our mechanical Newtonian world. So say you've got, let's take an example of a car, starts at rest, and then it's going to start accelerating. So we've turned the car on, we've put our foot down on the accelerator, we're burning up fuel in the car. So we're starting with some fuel, we've got some petrol in the tank, or maybe we've got an electric car, whatever, we've got fuel in the battery. And we're using some of that up. It's coming out of the fuel of the car, it's going into the engine, and then the engine is driving the motor, driving the wheels round, and then that is going into the kinetic energy of the car. So we've got a transfer of energy here, from the fuel through to the kinetic energy of the car. So, well, how quickly, how fast is this car going to be accelerating? How can we get 0 to 60 in the shortest time? That is the rate that we're transferring the energy in the fuel into the energy into the kinetic energy of the car. So we've got the amount of energy that's being transferred, which of course is in joules, but it's like how quickly is it happening? So joules per second, and that's our watts. The unit of measurement for power is watts, symbol W, which is joules per second. So yeah, that's what we're wanting to try and quantify. Now we can measure a lot of these things. We could measure how much fuel has been used. We'll have a certain number of joules, say X, that has been used in the fuel. We can measure and calculate the kinetic energy that we've got at the end of it with some other setup here, Y. I mean, if everything's 100% efficient, this is the other part of this that we want to look at of efficiency, is then X will be equal to Y, because we've got conservation of energy and all of our fuel that we've used has gone to where we want it to go, as in it's gone into the kinetic energy of the car. Now, of course, this isn't going to be the case. We're going to get some losses going on. There's going to be losses in the engine. There's going to be losses against friction on the road, against air resistance, things like that. Sometimes you might have seen these quantified in these things called Sankey diagrams, S-A-N-K-E-Y. I think that's what it's called, Sankey diagram. I don't tend to use these very much, but they can be quite good when you're getting into it, of illustrating what's going on. Like you're setting a width here on a big arrow. That's your total amount of energy. You're thinking of the height of this, and this big arrow then gets broken up. So you've got most of it, say, going into the kinetic energy of the car, but some of it might break off and sort of draw little arrows going off to the side. So you might have 90% goes into the kinetic energy, and then you might have, I don't know, 10% going into losses. I'm just sort of making this up as I go along. So it's the straight on bit here is the useful energy, and then you've got these losses that are coming off to the side, and this 90% is then our efficiency. It's how much of the output, Y, is the useful part of the total input. So useful output, which is Y, because that's all gone into the kinetic energy, divided by the total input, because that's everything that we've used. And that is going to be our efficiency, and that is just the percentage. So these are all the things that we've got going on here. Of course, we can quantify these things in different ways as well. We could start talking about this in terms of force, because if we know what our final kinetic energy would be, we could do all of this off of Newton's second law and say, well, if we've gone from 0 to 60 in, I don't know, however many seconds, 5 seconds or whatever, then we've got a certain acceleration that's gone on in this time. We've got an acceleration of 12 meters per second, 12 meters per second squared. That's our acceleration. So we can work out what the force must have been if we've got the mass of the car. So we divide the 12 by the mass. Multiply the 12 by the mass, and that gives us the force. And then we can quantify things in that way. We can bring it back to our dynamics in all of this and say, well, that must have been the driving force of the engine. That if we got 1,000 kilogram car, we can say, well, we've got a 12,000 Newton driving force on this car. I mean, that's quite a heavy car, but you get the idea. So we've got that going on, and that would then fit in, because we could say, well, the force times the distance, that is our energy transfer. So if we do force times distance, that's our work done, and we've just worked out force here from Newton's second law. And then you divide that by the time, and then we've got power. So that's work done over time is power. But then we could rewrite that as force multiplied by distance over time, and distance over time, of course, is velocity. So we can say force times velocity equals power. That's another way that we can write this down if we've got a driving force of an engine. So it depends which way we're approaching the analysis here. Are we starting with forces, sticking in our world of dynamics, where we're looking at forces, velocities, that gives us a power, that could then bring us back onto energy, or are we starting with energy and then saying, well, what did we start with? What did we end with? How long is it taken to move it? And then that's giving us a power off of that. So yeah, different ways of looking at it, really. I think the only other thing that I'll mention on this, just because so many people ask about it, is what's going on with horsepower. You hear this a lot in cars, where they say you've got a certain horsepower. You might buy a car, typically a standard small or family car might be, I don't know, 100 to 150 horsepower, something like that. So you'll see that as the spec on the engine. I mean, supercars, some of those crazy supercars, I mean, they're getting up to around 2,000 horsepower if you're right at the top end. I'm not sure they've quite reached that yet, but they certainly are a lot higher. So this is going back to the old imperial system. So from the British imperial system, before we went metric and we were still using all this crazy stuff with feet and inches and pounds and ounces and all this sort of stuff. And you can think of it as, well, let's go with this description of the work done per unit time. So if you've got, you can have a unit of work, so an energy unit, which is the foot pound. So that is moving. So pound is force, foot is distance. So you can still buy potatoes and things like that. You can get a pound of potatoes. You move that through a distance of 1 foot, just short of a third of a meter. Then you've got a foot pound. That's the amount of work. It's a force that you've moved through a distance. If you then do that in a certain amount of time, then you've got power, because you've got energy over time. So horsepower is 33,000 foot-pounds per minute. So that might sound a little, well, maybe not a little, arbitrary, very arbitrary, but that's what horsepower is. I mean, this goes back to when James Watt, the guy, I'll do a separate video on him, the guy who Watts are named after, and he was trying to compare the output of engines that were being built. So this is right back in the early days of engines being built, and he was trying to compare the power output of an engine to a horse lifting water out of a well. So if you've got some horse tied to a bucket lifting water out of a well, and it's lifting up a certain amount of water through a certain distance in a minute, and he was going through this, well, if a horse can do 33,000 foot-pounds per minute, which apparently is reasonable for a horse. I mean, people back in the day knew what horses could do when it came to lifting things. It was talking their language, really. This is what you can expect to get out of a horse. This is what you can expect to get out of an engine. So if you've got a 1 horsepower engine, it's going to be lifting the amount of water from a well that you'd expect a horse to be able to do. So that's where it all came from. And then it's stuck. You know what it's like. You get these things, people start using horsepower for engines and cars and things like that, because of course cars were coming out over 100 years ago now. People in the UK and in America, where we were still using the imperial system, unlike the French and other countries that have moved on well before we did, the horsepower was still a common term, and that was what was being used for describing car engines. And it's just stuck. It's hard to get out of these things when you start using them. I mean, we see what it's like. Everyone still talks about miles and giving their height in feet and inches and their weight in stones. So it's easier said than done to change it once the system is stuck. But still, that was just an aside on the end of all of that. The main thing with power is we're going to use this in a lot of different contexts, and there's a lot of different ways of working it out, because it always comes back to okay, we can say that power, great, yeah, it's the joules per second, it's how quickly we're moving energy from one place to another. But it immediately raises the question of, well, how do we measure the energy? How do we know what we started with, and how do we know what we ended up with, and how do we know how much we've lost in the meantime? This is going to vary from circumstance to circumstance. So the actual concept of power is pretty straightforward. The actual application of it is more difficult because it's varying so much. I mean, we'll see this in a few topics' time when I start looking at simple machines. You know, if you've got a pulley or something like that, we can say theoretically from the design of a pulley how much we would expect it to be able to lift for a particular input force. So we can go out and empirically measure that, and we can work out what the efficiency is because it won't be able to lift it. So we're going to keep on revisiting this. It's not a closed section. It's not a closed topic, power, because we have to continually work out what we're doing based on the context. But at least in this, we do have some stuff that we can use straight away in our classical mechanics, because we've got this force times velocity is power, force times distance over time is power. Yeah, we've got various things that we can do. We can work out kinetic energy, we can measure velocity, we can measure the mass. There's a lot of stuff we can already do in classical mechanics without worrying about how it's going to change in the future.